Okay, now this is the third part of lecture number 6. It is about a moving conductor in a static magnetic field. So in Faraday's law, what we studied so far is a case where the loop is stationary, not moving, but the magnetic field is varying with time. This is another case where we have the magnetic field is stationary, like static, but the conductor is moving. When a conductor moves with a velocity u in a static magnetic field, as shown here, a force, magnetic force, will be exerted on the electrons or the charges in that conductor. We know that the expression for the magnetic force equal the charge multiplied by the velocity cross product with b. So in this case, the velocity is in this direction and the magnetic field is going out of the slide or out of the screen. So you can apply the right hand side rule to find out the direction of the force. So if the charge is positive, u, b, so it will be, the force will be going in the down direction, which means that the electrons will be moving in the up direction. When we have this situation, there will be some charges, electrons accumulated on this side of the conductor, and they are leaving holes on this side of the conductors, which will create a magnetic field, an electric field in that direction. So the magnetic field in this direction is trying to bring the electrons back, while the force, the magnetic force in this case, which is like repelling the electrons to this side, the electrons will accumulate. The more accumulation we have, the stronger the electric field will be till we reach the equilibrium. At equilibrium, the electric force equals the magnetic force, and this is the condition for equilibrium, and this is very similar to the Hall effect that we studied before. So in this way, or like in this condition, we can calculate the potential difference between the terminals of the conductors. The potential difference at equilibrium equal E dot dl. We have E equal U cross B. So the potential difference between the two terminals equal U cross B dot dl integrating from point 1 to point 2, and this will give us the potential difference between those terminals of the moving conductor in a static magnetic field. So the time variation here is like a moving conductor, not a variation in field with time. And this case also is generating electromotive force. One application for this phenomena is Faraday's disk generator. Like consider this schematic or this picture where we have a source of magnetic field from north to south. So the magnetic field is going inside the screen, and we have a rotating disk. So we can draw like the same pictures that we have here. It can be drawn like this. We have like a disk rotating, and we have along certain line or just like in some area of the disk there is a magnetic field. So in this case, let me just bring the bin. In this case, the magnetic field, okay, let me bring this again. So in this case, the magnetic field exists in this area because this is where the magnet is. There is no magnetic field outside this region. So if we are back to the pointer, if we are like considering just this radius line. This radius line will cut the magnetic field. So it's very similar to this case, but it is a radial movement rather than like a linear movement. So this line of the disk, this radial line of the disk will cut the magnetic field, and because of this cut, or this, if we have like a constant speed, there will be a potential difference along those 2 points. If we put brushes, one brush at the center, one brush at this side, as shown here, we have a brush at the center, we have a brush at this side. When this line is moving, so this line after a while, okay, so this line is here now. After very few moments, it will be moving to this point. So this motion here will generate a potential difference between the brushes. After this radial line moved away, another radial line will come in, and the continuous motion will cause like a continuous potential difference between the brushes, and this way we can have a dynamo. So if we want to calculate the potential difference generated by this dynamo, we can just calculate the EMF, electromotive force. The EMF in this case equal what we had in the previous slide, U cross P, because U cross P at equilibrium equal E dot dl. So we are integrating from this point to this point, from r equal 0 to r equal B in this case. So the potential difference will have this expression depending on the angular velocity, the magnetic field quantity, the radius of the disk. We can find the EMF generated by this dynamo. Another case, or like let us talk about like the general condition where we have a moving conductor as well as a time varying magnetic field. In this case, the time varying magnetic field will generate EMF, and this is called induced or transformer EMF. The motion of the conductor, in this case the conductor is a circuit, so it's a closed contour. It will cause like a flux cutting EMF. The total EMF in this contour or in this circuit or in this loop equals the sum of the two. The motion, or like the motion of the contour, can be translation, so it can just move like in X or Y or Z direction, just translate. It can be rotating, it can be a change in the contour shape, so it can be like converting like a rectangle into a triangle, or a rectangle into a square, or just deforming. Any kind of motion for the contour also is considered in this case. With some lengthy derivation, we can find that the total EMF, both transformer and flux cutting, equal d phi by dt. Phi is b dot ds, and we have the negative of derivative with respect to time of the flux equals the EMF. So inside the integration, the magnetic flux or the magnetic field can be varying with time. S can be varying with time, and the dot product integrated along the surface of the contour is the flux. The time varying of this total quantity is equal to the EMF. Let us consider this example here. We have an h by w rectangle, like this one rectangle. It has like a height equal h, a width equal w, and it is a loop. So it is closed. From this side, it is closed by a brush. One brush is like connected to this terminal. Another brush is connected to the other terminal. It is situated or placed in a changing magnetic field. So we have a time varying magnetic field that is in the y direction. This is the y direction. The normal of the loop initially makes an angle alpha with AY. So if we are looking in that direction, so we are looking in that direction along the x-axis, this is what we're going to see. We will see a magnetic field in the y direction, and the loop is rotating in this plane, rotating around the x-axis. It is rotating around the x-axis. Originally, what we have an angle, as seen here, making an angle alpha with AY. So this angle at the beginning equal alpha. The angle between this is AY and this is the normal to the loop. So this is the 3D shape, and this is sort of like looking into the x direction cross-section or perspective. We need to find the induced EMF under two conditions. When the loop is at rest. In the beginning, the loop is at rest. We need to find EMF. Then when the loop starts to rotate with an angular velocity equal omega, the same angular velocity of the magnetic field. And the rotation is around the x-axis. So in this case, this is AY. So this is, sorry for this, I'm just writing with the mouse. So this is AY. So X would be going out of here. This is the X direction is going out of the screen. So this is the setup at the beginning. This angle here equal alpha. We would like to calculate the EMF, induced EMF, under the first condition where we are making AN is making an angle alpha with AY, and the loop is stationary. Number two is the case when the loop is rotating with angular velocity equal W. As I always advise, I would like everybody to pause the video right now and try to solve this problem yourself. Then after like solving it and doing effort, try to understand, you can go back to read like the expressions or whatever. After like trying and doing my best to solve this, you can unpause the video and continue to see the solution. Now I would say that I hope most of you had tried to solve this yourselves. Now we would like to see the solution. The first condition, when the loop is stationary, EMF in all cases equal minus d phi by dt. In this case, phi equal b, this expression as a function, this is b in the AY direction, dot product with ds, because the field is constant. It is not depending on x nor y nor z. It's like DC, sorry, not DC, but constant amplitude, just varying with time. So the field across all the loop surface area is the same. AY dot AN. This is very important to try to find. So this is AY and this is AN. The dot product of them equal cosine alpha. So we have cosine alpha from the dot product. WH equal S. B naught is constant. The only variable here is sine omega t as a function of time. So we just do the differentiation and we come up with the expression of the EMF under the stationary loop. So this is the first part of the example. The second part is when the loop is rotating. So it's the same things that we need to find. We need to find phi, which is B dot ds. We know B, the expression for B is this one in the AY direction. S is WH, and we have AN. The challenge here is to calculate what is AN dot AY. Remember that this is a rotating loop. So let us go back here. So this loop is rotating this way. So the angle between AY and AN is varying. So when the loop is rotating, AN also is rotating with an angle equal, with a velocity equal omega, angular velocity omega. So at any time, the angle between AN and Y equal alpha plus some value depending on omega. Omega here is like a radian per second, so it will be omega t. So the variation here will be omega t as well, because the angle will be whatever plus omega t, because it is varying. So it can be cosine omega t, it can be cosine omega t plus alpha. It will not make a difference. So we have one time dependence because of the field, another time dependence function or component because of the rotation. We just do sine cosine, the sine cosine multiplication. It will give us sine 2 omega t divided by 1/2. So this is the expression for phi. The EMF equal minus d phi by dt. So we just apply that and we get the expression of EMF. So this is the end of part 3, and I think for this week I'm just stop here and continue the rest of lecture number 6 next week inshallah. Assalamu alaikum.